Hi everyone, welcome to What's Up Physics. I'm Aishwarya and this is the second part of our Newton's third law lesson where we're going to go over some AP style practice problems. If you want to go back to the lesson video, it's linked in the description box. Let's get into it. Problem number 1. Two boxes M1 and M2 are in contact with each other. The mass of M1 is less than that of M2. When an external force of magnitude F is applied to M1, the system of boxes accelerates at magnitude A. So I'm going to draw a quick picture of that. We have M1 here, and then M2, which is greater in mass than M1, and then a force of F is applied to M1. Okay, part A. If a force is applied to M2 instead of M1, does its magnitude need to be less than, equal to, or greater than the magnitude of F for the system to accelerate at the same magnitude A? Explain. Okay, so from Newton's third law, F equals ma, we know that if the mass and acceleration are to stay constant, the force must also stay constant. And so this force must be equal to F for the system to accelerate at the same rate A. When we push the system from the other side, like this, regardless of how the contact force in between the boxes might change, the behavior of the system as a whole will not change. Since we want the same magnitude of acceleration and we have the same mass as before, F must also remain constant. So we're going to say equal to. Okay, and part B. If a force of the same magnitude is instead applied to M2, is the contact force greater than, equal to, or less than the contact force in the scenario above? Explain. Okay, so I'm going to draw a quick scenario of that too. We have M1, M2, and then the force is now applied from this side with same magnitude F. So we're given that M1 is less than M2 in terms of mass. When F is applied to M1, it takes less of that force to push M1 and more of that force to push M2. Or in other words, that contact force is pretty high. In the second scenario, when F is applied to M2, most of that force is spent pushing M2 and less of that is pushing M1. So in other words, the contact force is smaller between the two boxes. So we're going to say less than. Problem number 2. 3 boxes are connected by a string and pulled by a force Ft to the right. Part A. Which of the strings has greater tension, T1 or T2? Okay, so to figure this out, we can draw quick FBDs for each box. So let's start with M1 over here. Gravity and normal force. And then it only has one force pulling it horizontally, which is going to be the force of tension in T2. So I'm going to write Ft2. Okay, next we can draw M2. Again, we have normal force and gravity. Okay, now for this one, we have two forces pulling it horizontally, T2 to the left and T1 to the right. Now, which one is going to be greater? Well, we can look at the whole system for a second. We know that Ft is the external net force on the whole system, and it pulls the system to the right, meaning it accelerates to the right. So each box has to accelerate to the right individually, meaning that the net force on M2 has to point to the right as well. And what this means is that Ft1 must be greater in magnitude than Ft2. So let's draw Ft2 here, and then Ft1 is going to be greater. Okay, and then for M3, I'll draw that up here. We have gravity and normal force. We have Ft1, which, this arrow technically needs to match the length of this arrow, but I just don't have space. So there's Ft1, and then here's Ft, which is going to be the greatest. Okay, so just by looking at the lengths of the arrows, we can see that Ft1 has a greater tension force than Ft2. So there's going to be greater tension in T1, the string of T1. But we honestly don't even need FBDs to figure this out. We know that all 3 boxes accelerate at the same rate, and Ft1 is responsible for accelerating 2 boxes, while Ft2 is only responsible for accelerating 1. So Ft1 must have greater tension in order to accelerate that greater mass. Part B. If the acceleration of the system is A, write an expression for the magnitude of Ft1 in terms of M1, M2, and A. Okay, so since T1 is pulling specifically on M2, we can apply the second law to M2. So we know the net force on this box is going to equal Ft1 minus Ft2. So I'm going to write that out. F net equals Ft1 minus Ft2, and then this is going to equal M2 times A. Okay, so since we're trying to find Ft1, I'm just going to isolate Ft1, M2A plus Ft2. Okay, and now we need to find what this is in terms of M1. Okay, so we know that T2 is the only net force, or is the only force pulling on M1, meaning it's the net force on it. So we can write FT2 as MA, M1 times A, because it's the net force on M1. Okay, so this is our answer. And if you want to take it a step further, you can pull out the A. There we go. Problem number 3. Mariah and an elephant run towards each other. The elephant is 100 times the mass of Mariah and runs at double the speed. When the two collide, is the magnitude of the force of the elephant on Mariah greater than Mariah's force on the elephant, equal to Mariah's force on the elephant, or less than Mariah's force on the elephant? Okay, there is and always will be the same correct answer for any question like this. When two objects collide, regardless of their mass, speed, acceleration, or any other factor before they collide, the objects will always exert the same force on each other. The force of the elephant on Mariah is equal in magnitude to Mariah's force on the elephant due to Newton's third law. Every action has an equal and opposite reaction. But poor Mariah, that must suck. Alright, you've reached the end of our practice. Our next video is going to be on elevators, so be sure to stay tuned for that video. If you found this video helpful, please be sure to like, share, or subscribe, and see you next time. Bye!